Welcome to this video presentation for one of our recent papers, published in Environmental Pollution, titled Estimating Primary Vehicular Emission Contributions to PM2.5 using the Chemical Mass Balance Model, accounting for gas particle partitioning of organic aerosols and oxidation degradation of Hopanes. I am Wong from the Division of Environment and Sustainability of Hong Kong University of Science and Technology. Vehicular emissions that are generated from combustion of fuel are one of the major sources of urban air pollution. Of the various air pollutants generated, the fine particulate matter, or called PM2.5, referring to particles with diameter smaller than 2.5 micron, is the most concerned pollutant because of the clear evidence for its health impact. Vehicular PM is primarily composed of elemental carbon, EC for short, and also organic aerosols. EC is also known as soot, while organic aerosols are made up of thousands of individual organic compounds. Some organic compounds are uniquely found in certain kinds of sources and therefore can be used as tracer to calculate the contribution from the corresponding source to the ambient PM. As an example, Hopanes are the group of C27 to C35 organic compounds specifically found in motor lubricating oil. These compounds have traditionally been used to track the emissions from gasoline vehicles, while EC is commonly used to track diesel vehicle emissions. A tool that is commonly used to quantify source contributions is called receptor model, which is based on a chemical mass balance approach represented by this equation here. It assumes the tracer concentrations we observe in the ambient air is equal to the sum of the contributions by different sources, and because each source has a unique tracer to organic aerosol mass ratio, the organic aerosols contribution by individual sources can be calculated using statistical methods. For many years, this model has been accused of being inaccurate because of two main reasons. First, the organic traces are reactive in the oxidizing atmosphere. Second, the organic aerosols are not inert once emitted to the atmosphere. They undergo partitioning between the particle and gas phase, a process depending on temperature, background aerosol concentration, and the volatilities of individual organic compounds. These two processes certainly change the chemical mass balance and hence bias the source contribution estimation. So the objective of this work is to investigate how these two atmospheric processes are going to affect the apportioning of PM to vehicular sources. To achieve the project objective, we analyzed the organic and elemental carbon and Hopanes data from PM samples collected from two locations in Hong Kong. One is a roadside location in Mong Kok, and the other is a general station in Yuen Long. Specifically, we used the Chemical Mass Balance Model, or CMB in short, to quantify the contributions from gasoline and diesel vehicles. To examine the effects of gas particle partitioning of organic aerosols and oxidation degradation of Hopanes on the results, we ran and compared the model results with and without incorporating the two atmospheric processes, using the two equations shown here. The left one is used to describe the fraction of organic aerosols that remains in the particle phase, while the right equation describes the fraction of Hopanes remained after oxidation. And here are the results. For each pair of bars here, the left is from the traditional CMB where no atmospheric processes is considered, while the right is the modified CMB with the atmospheric processes considered. We can see that in Mong Kok, regardless of atmospheric processes, diesel vehicles play a dominant role in contributing vehicular PM, a result that is consistent with previous field measurement studies. The result in Yuen Long is totally different. The modified CMB gives a gasoline versus diesel contributions that forms a stark contrast with traditional CMB. It indicates the vehicular contribution change from being diesel dominant to gasoline dominant, and because of the combined effect of high organic aerosol concentration and lower temperature in winter, which favors the partitioning of organics into the particle phase, the vehicular PM contributions increases by 73%, as shown in the modified CMB. These pie charts show the breakdown of the apportioned vehicular PM composition. The upper row is from the traditional CMB, and the lower is from the modified CMB. We can see that in Mongkok, EC from diesel vehicles is the largest component, and for the Yunnan samples, organic aerosols from gasoline vehicles dominates the vehicular PM, and this is notably different from the results obtained by the traditional CMB, which shows that diesel EC is the most important component. The difference in vehicular PM composition in different locations does have a health implication in exposure to traffic-related air pollutants, and the results can potentially help devise more pinpoint strategies and management plans to minimize public exposure to traffic emissions. To sum up, we developed a method to incorporate the gas particle partitioning of organic aerosols and Hopane oxidation in CMB modeling to more accurately apportion vehicular PM. Our results show the modified CMB apportions lower PM from diesel vehicles by 1/3, while triples the contribution by gasoline vehicles compared to the traditional CMB. Last but not least, the methodology can be applied in CMB modeling of atmospheric aerosol samples from other urban locations, serving the need of better control policy making to mitigate PM pollution by on-road vehicles. And that's it. For more details, please feel free to read our paper, and thanks for listening.